Yeah. I was like, yeah, it was amazing. There we go. Go on. No, it was unbelievable. Okay.
Use art into like all of their curriculum. It's really cool. So we're gonna, if it's okay with everybody, stay, maybe start lab a little bit early, but then stay, instead of having that 15-minute break, can we stay until 12:30? And we'll run through the sort of presentation of the lab, and then I'll leave you guys to finish exercises. And I'm sorry, I'll try to be better about getting you your lab assignments by Thursday afternoon, the latest. Sorry, it took me a little while this week. I had to put map projections for a long time to try to make it hard for you. I bet you all appreciated that, right? Okay. So we stopped, we didn't make it all the way through this lecture last week. So let's see if we can, I thought we'd go back and kind of start here. Andrew pointed out that this is actually a really good illustration, having the orange on this front slide, because the concept of, oh, there we go. We've got a demonstration back there if you want to look at something. Orange field. The concept of map projections, we talked about this developable surface. If you think about like how you're going to peel an orange, it's the same idea. How are you going to go from that sphere to a plane? And depending upon how you go about it, you're going to have these different cuts and warps in your peel, but there's lots of different approaches. No matter what you do, though, you can't end up with that same full peel at the end, unless you're back in the sphere shape. So whenever we're doing this, we're going from our spherical coordinates to our flat coordinates, and we're always going to have to use different approaches to do it. But whatever approach we go about, we're always going to have the problem of we have a different amount of Earth surface that we're trying to project onto a plane map surface. So this concept here that distortion is inevitable is really kind of the big thing to point out whenever we're thinking about map projections. So here's that slide we looked at last week where the points where our map surface, our planar surface is we'll be needing to compress the amount of area that we're representing when we put it onto a plane. Sorry. I turned it off when I was babbling. Oh, good. Okay. Well, fortunately, it's a little bit of review.
What's that?
It's reviewed. So. Okay, thanks, Jeff. So remember, when we're trying to represent this portion of the Earth's surface on our map, we're compressing distance. But when we're representing this portion of the Earth's surface, we're actually going to be stretching it. So there's always going to be differences in our representation of the surface depending upon where we are on that plane. It's not constant. So not only is it distorted, it's also going to be differentially distorted in different places in your projection. Okay, so you remember that we describe our projections by either, or usually by both, the type of error that they're designed to minimize and the method that we're using to extrapolate that curved surface onto the plane, the type of what we call a developable surface. Again, the only way that we can actually represent all of our basic geographic features accurately is through a globe, so we can only preserve some of the properties. Here are those developable surfaces
again. Which we call, instead of we call this a cylinder instead of a, what's that shape? That's not a cone, that's a sphere? What is it? Sorry, guys. Cylinder, thank you. That's a cylinder, cylindrical. I need to explain one thing about myself. I have twins that are 1-year-old, and so I frequently don't sleep for more than 3 hours at a stretch. So if I'm fumbling over my words, I'm just going to give you that. Okay, going back to my presentation. Okay, so conic, if we're using a cone, and plane, or azimuthal if we're using that flat surface. So I like this this graphic because it breaks everything down for you. Sometimes you can get overwhelmed by all of the different types of map projections that are out there. There are hundreds and hundreds of map projections. You don't need to know all of them. You just need to understand, like, theoretically how they're broken up and what it means if you're looking at a cylindrical normal projection versus a transverse. So it depends upon where that cylinder is coming around. And if you've got your main meridian going through the equator or going through a line of longitude. So that's going to make a difference in your projection. I don't need you guys to memorize this at all, just to have it kind of understood so you can refer to it. Again, remember that these distortions can be really great. If you look at the difference between a Mercator projection, its representation of distance, versus the Albers equal area projection and its representation. The Mercator is trying to preserve shape more than it is trying to preserve distance. And you can see how far off we are when we're trying to actually measure distance here. So just to have some of those, again, that you should know, I'm going to show you kind of the two that I think are the most important, but here are some of those big categories and some of the main ones that fall into the conformal, so the shape-preserving ones. Remember, the Mercator is trying to preserve shape. Transverse Mercator is another type of Mercator, also with shape, and the conformal conic. Equal area is trying to preserve area. And depending upon what type of projection they're using here, the area will be preserved in different parts of the globe. So here with the Peters, we're preserving area better in the equator. Which, don't you guys think that's kind of surprising when you look at that map? Doesn't that look kind of distorted to you? Exactly, because we're so used to this, like the standard maps that are used have all been developed in European countries in the northern hemispheres. So most of our maps are actually exaggerating the size of countries in the northern hemisphere and kind of shrinking the ones around the equator. So we all are sort of trained to see the world in particular ways because it's been represented in particular ways in our map projections. But it's not necessarily an accurate portrayal. Azimuthal, again, really much more commonly used in polar areas where it's hard to get those projections. And then there are these other ones. The Robinson is one attempt at making a compromise projection. Some of these, like the Robinson, doesn't actually use the normal projection onto different developable surfaces. It uses a combination of different mathematical equations. So there's another group, but you don't have to worry about it because mostly they're used for very particular purposes. So here's just one example I thought was interesting to show you what sort of one area. This is Greenland, and what it looks like, or how different it can look depending upon the projection that's being used. I think it highlights the importance of thinking about your projection before you use it, before you start on a project. So whenever you're starting on a project, you have to think about choosing what your map projection is going to be. So what your area of interest in is probably going to be the first point. So if you're working in North America, for example, you're going to choose a projection that's focused on minimizing the distortion in that area. With every projection, the points where your developable surface is going to touch the sphere is where your distortion is going to be most minimal. The points of contact of those standard parallels. Sometimes there's one and sometimes there's two. It depends upon what projection you're using. And the further you go away from those points of contact, the increased distortion. Just showing sort of a better example. The Lambert conformal conic is one of the most commonly used ones in the US. It's the basis of a lot of the state plane systems. And what you can see here, these are constant 5 degrees circles that are 5-degree radius circles. So it's showing you how distortion is changing as you move across the surface. So with the conformal conic, it's preserving the area best between these two standard parallels. So it's really best for maps that have a stronger east-west than north-south orientation. So you'll see that a lot of your longer states are using the conformal conic as the projection system. And this map here is showing you how in between these two standard parallels, this one and this one, that's where you're having the least amount of error. So you can think about whenever you're working with a projection, wherever those standard parallels are, the area in between those two is going to be the best representation of reality. And as you move away from them, it's worse. Okay. The other commonly used one in the US is the transverse Mercator. There it is, a cylinder. How those things sometimes look. And in this one, you're only using one central meridian instead of two standard parallels. So here it's showing you how your error is least going in a north-south direction. So it's better if you're working with states that have a longer north-south dimension than a east-west dimension. You can see here how much that distortion increases as you go farther away from that one central meridian in this map up here. Okay, so in the US we use most commonly either the UTM, a universal transverse Mercator system, or the state plane system. You guys are probably more familiar with this now that you've been working on your labs. And we're going to talk about each one of these in turn. So transverse Mercator, or UTM, not only is really commonly used in the US, it's commonly used everywhere. It's probably the most common projection system that I work with. And what it is is it takes the whole world and it splits it up into 60 different zones. Each zone is 6 degrees wide, and the distortion within each one of these zones is minimal. So it's really convenient that you can work in this whole wide range with one projection system. It's hard. You can't really work with 2 UTM zones because the whole numbering system changes from one zone to another. So you don't want to work between zones. Best if you're working within a single UTM zone to use it. In the United States, this is showing you all of the UTM zones that we cover here. So North Carolina, for instance, could be kind of tricky to work with if you were trying to work with the entire state because you're crossing from UTM zone 17 here into UTM 18. Sometimes it's okay if you're crossing just a little bit and you still want to continue to work with UTM. It's not going to be too bad. Your distortion is going to be increased over here, but you could still work with UTM 17 and just cross that boundary. You'd be outside of sort of the standard area. So the way that UTM zones work, I think I actually should go back to this one, is that along the equator, you split between UTM zone north and UTM zone south. So if we're in UTM zone 17 north up here, down in this off the coast of Peru would be zone 17 south. So you're still 17, you just designate if you're in the northern hemisphere or the southern hemisphere by that north or south extension. Inside of a UTM zone, your values are in meters, and you're always going to have positive values, which is kind of nice. You can see why working with a UTM zone is better than working with a geographic coordinate system when you're working with units of measurement that you can understand that means something on the ground, meters instead of degrees or minutes or seconds. The way that a UTM zone is organized is that you have an origin point down here when you're working in northern zones. This is a point where your northerly value is 0 and your east value is 0. As you move north in a UTM zone, you talk about you're moving northerly, you're northing. Your values for your northing go up. You're going from 0 here down to 4 million. Almost 5 million up here. So you always know which direction you're going in. If you're going north, your northing values are going up. Sorry, hard to say that word today. And east, if you're moving in this direction, if you're moving east, your values are also going to be going up. So that's a really convenient thing to know when you're working with the UTM zone. Which direction am I going in? In order to maintain those positive values when you're working with a southern UTM zone, your point of origin is over here, but your northerly value starts at 10 million. So as you go south, that number is going to go down. Again, you have a central meridian in these zones where your distortion is going to be the least along that central meridian. But you don't really have to worry too much about distortion if you're within one UTM zone. Okay? Good to understand UTM zones because you will probably use them a lot. When you're working in the U.S., working with state plane systems is great, especially if you're working in a state that only has one state plane system and you're not going to have to go back and forth in between them. Mostly local governments will work with state plane systems because those local geographies are going to have much less distortion. Depending again on what state you're in, it's going to depend which projection system is being applied. Remember if you have like a northern, California for instance is going to use a transverse Mercator because the distortion north-south is going to be less. But North Carolina is going to use the Lambert conformal conic because the distortion east-west is going to be less. There are, as you guys probably have discovered when you start searching through ArcGIS under the state plane systems, there's lots and lots of different versions of them. Remember that there have been updates to datums over time. So the original state plane systems all used NAD 1927. And they've mostly been updated. There's a NAD 1983 now. The other thing that has happened is that we've gone from sort of a standard of using feet in the US to moving towards using meters to be on sort of the more global metric system. But there are feet versions of NAD 83 sometimes, so just always be careful to pay attention to what you're working with. Did you guys know that there are different conversions between feet and meters that are applied? 1 meter is like 3.08, and then it has a whole bunch of other decimal places after that when you're converting between feet and meters. In the US, we use a standard, we round it, but internationally, we use a much longer, many more decimal places. So even the conversion between feet and meters can be a confusing thing. Yeah. No, I haven't stated anything about that. It's okay. Here's a map of all the different state plane zones. And again, showing you where you're more likely to see a Lambert conformal conic versus a UTM zone like in New York. And then Alaska, our outlier, which is using an oblique Mercator because it's in such a different area. Okay, you guys have any questions about that? You feel like you're getting a grasp on projection systems? A little bit? Not at all? Okay. So when we're working in GIS, we're frequently keeping things in GCS and displaying it in GCS. This is just showing you an unprojected lat long map. And when we do that, we're using sort of a Cartesian version of lat long. But it's not really the best way to look at anything because it's based upon false assumptions, which is that the distance, latitude and longitudinal distance are constant, which we, as you guys remember, know that that's not true when we're working on our sphere. Remember the difference between a degree of longitude at the pole versus at the equator is hugely different. So there are problems when we're working with GCS, and especially when we're working in a planar system, working with GCS can cause all sorts of problems because it's distorting everything. It's distorting all of those things that we're trying to minimize the distortion in. So it's essentially why working with a projection is a lot better when you're working in a planar system. This is just showing you those 5-degree radius circles and how great our distortion is as we're moving to the poles here. So whenever you're really doing analysis in GIS, it's really better not to work in a geographical coordinate system. Always better to work in a projected coordinate system. Make sense? So why is it better to work in a projected coordinate system? Okay. So we've made it through our projection lecture. You guys should be relieved. I kind of distilled this from, I had it as 2 lectures before. I've distilled it down to 1, so it was a lot more information before. But just some of the key concepts that we've gone over, starting last week, the field of geodesy, which you guys can all go into. It's an active practice, trying to better measure the geoid, better create an ellipsoid model of the Earth. You guys remember what the ellipsoid is? Yep, and the geoid. What is the geoid representing? The surface of the Earth, what it would look like if it was all at mean sea level. And you're seeing the anomalies based upon gravitational differences. Yeah. So it's that funky shaped ellipsoid. Is the Earth a sphere? No. What do we call it? A spheroid, because it bulges because of centrifugal force. That was Isaac Newton, in case you want to know who thought about those things first. Probably actually not. Probably the Greeks had figured that out too. I'm not sure. And then we talked about all these different map projections, how we're going from our three-dimensional model of the Earth, which is the only way to accurately capture all of the different properties of the Earth, to go to two-dimensional so that we can better measure things. We talked about different projection types. And we always need to remember that whenever we're using a projection, we're introducing some form of distortion, so we have to think about what projection to use in order to minimize distortion, and select the best projection for our area and for your objective, if you're thinking about shape or size or distance. And we talked about some of these common projection types and the concept of a compromise projection. So I like that, again, this is a nice sort of summary table showing you some of the advantages and disadvantages of different projections. It's interesting to go through. Again, remember that globe is just fantastic in keeping all of the properties correct. But it's not suitable for mapping, right? We end up with all sorts of problems if we're trying to use it to map. And you can go through and look at these more carefully and think about if you wanted to work in a particular area or at a particular scale, what would be a good suggestion for different projections to use. Again, always remember that you need to report the datum that you're using when you're using a coordinate system. But if you're using a world datum like WGS, or if you're using a local datum like NAD, that always needs to be included when you are talking about your coordinate system. Because if you're using a different datum, you're going to change the coordinates. Spherical coordinates, this lat long can be represented, remember, in degrees, minutes, seconds, or in decimal degrees. It's always important to remember that the length of a degree isn't constant. And we talked about projection, planar coordinates. After you go through projection, the most commonly used ones are these UTM and state planes in the US. It's always important when you're giving information about what spatial reference system you're using when you're using a projection, that you include all of the key components of that as well. Again, what datum is being used, and then if it's using a central meridian or standard parallels. Those are all contained in ArcGIS in that sort of summary table when you go under properties and it shows you the coordinate system. All those key components are included in there. Okay, so if you guys remember, in one of our first classes, I gave you a worksheet, and now is a great time to finish that worksheet. Michael, why don't you and Orion work together since David's not here today? Yeah, that's why I kept it. You guys, sorry. Okay. Allison.
It's like, alright, yeah. Start with the flow, right? That's what they did was they uncurled it. It's distorted everywhere, but China's kind of like that's the center of our dance. That's how they pronounce it.
Are you guys all okay?
Oh yeah. They got the skeletal. So fairly I was just sitting by the side of the road and I was like gearing up to be like, alright, I'm just gonna have to walk class. It's like 20 kilometers. And like, it was already late at night. No, I was like sitting by the side of the road with like walking line. I was like very lost. And then these guys were the rapid fire the ones that were really So have you managed to unzip that's like old phone. You're supposed to click on the download.
Oh, okay.
Yeah. You don't have to.
Did you guys figure out, remember last week, you were asking me that question about minutes?
Try it. I don't like looks of it, but try it.
I figured it out. I mean, it's been fine. Because, 360, you got 300.
So it's not, so the 750, so here, go to,
but then how many minutes you have in a day?
I'm gonna set the,
360 times 60. And then you divide that by the total minutes.
go to Google, you just get a WinZip trial and then you
It's not, that's not. So it works out. Yeah, you just have to do that. Extrapolate how many minutes.
Specifically go in here.
Oh, so like. No, wait, that would be right. So I kind of.
That should make it.
Once they're predictable, because that's as long as it's hours. So, but there's 360, how many minutes are there? So in the hour, so we have, so you got, well, 203 minutes, 21,600 minutes, divided by the total number of minutes on the day.
Only one of them's done fine. I think it's the other ones have some kind of projection.
Yeah, so you have to do minutes. Yeah, because here we.
Seconds divided by second, 20 minutes divided by minute. Break down. Are you guys done? Yeah. Okay. Are you guys done? Okay. Yeah, and actually, Caroline asked a question about on your lab assignment with the river basins go extend beyond the state. That's okay. I don't want you to clip it down to the state. You can just have them extending beyond the state in your final map. Just make it look okay.
Is this alright? I don't know. As far as the bases.
Yeah, you might want to. Are they outlined? Here. be like that.
I'm not outlined within the state. I need to just go back and look and find. I
Okay, it's a little hard to see.
Oh yeah, no, the blue stuff needs fixing.
Okay. Yeah, it looks okay. Okay, is everybody done? Should we come back? Guys, I like to give you a break from just straight lecture because I know that it can be sort of exhausting to sit here and have me talk to you about things. Maybe somewhere in between. It's a nice break. It's a nice break. Okay. They're finding more and more that you guys don't really learn that much when you sit and I lecture at you for an hour, but only a little bit of that information. With each other and figuring stuff out is a much better way to learn. So I'm trying. I wanted to show you guys this website, the National Geodetic Survey website. It's where you can go if you really like this stuff, want to learn more about it, or if you need information like tools, transformations, for instance. Remember how I told you that sometimes you're going between one projection system to another one, and it can be hard. Maybe the transformation isn't actually stored in ArcGIS or in whatever program you're working with. You can go, every country should have a site like this where you can get those standard transformations that maybe aren't available in your program. You can also go to a geospatial summit if you really get into it. But it's really interesting stuff. I find it kind of cool. I wanted to see, I don't know if I can show you this one too. I'm supposed to plug this guy in. Maybe it already is. Let's see if it works. Oh, Will Ferrell, no. Gross. Might be more exciting than this Danish geodetic survey. Let's see if this is going to work. Okay, well, we'll do that one next time. Okay. Well, never mind. We'll go back to that. So I have heard a couple of complaints about Sakai. Colleen, I found out if anybody gets kicked off of your quiz because you got intermittent internet or something, you're supposed to just take a screenshot of the message, send it to me, and then I can send it on, or I'll just give you access to the quiz again. It's fine. Maybe you'll be able to get access to the quiz again on your own too. So don't worry about it. And I can't figure out why you didn't get feedback on your quiz, but I'll try to make sure that you do get feedback next time. But everybody did okay with the quiz. It wasn't. Did I tell you what it would be like well enough? You didn't have to go and. Thanks, Jeff. I'm stuck on.
You mean you wanted sound?
I wanted to do sound. And so I plugged this guy in here. That's this one. Did anybody else have problems with Sakai this week with the quiz or anything else, or have any feedback for me on how the quiz went for everyone?
Does anyone know what they got? Is it just me?
Yeah, my cousin.
Okay.
Yeah, it was supposed to release both your score and feedback to you. And when I looked at my settings, that's how it's set up. So I'm not sure why it didn't, but I'll release it to the grade book and see if it works that way. Okay, so does anybody have specific questions that they need for help on for while we try to figure this out for the labs that you want to ask me now, or? Yep. Okay.
Do you want us to put source information, or since you gave it to us?
Just put me down as your source. Yeah. For now. I can't reveal my sources yet. I'll reveal my sources on Thursday.
Do you want us to also like put down like what projection?
I want you to put down what final projection everything is in, and everything needs to be in the right projection. So write down the steps that you go through to get all your layers into the same projection.
In the right projection, the same projection.
In the same projection. Yeah, yeah, you're gonna have to play around with it to get them all in the same thing.
Surveyors have worked for decades
There we go.
to create a tremendous.
Okay, thanks, Jeff.
You just push buttons.
Okay. Yeah.
tremendously accurate reference system across the United States that helps define such things as property boundaries and floodplains and is used in many other applications. Today's geodetic datums are defined using data that has been collected since the 1800s and augmented with data and models that use today's state-of-the-art technology. Advances in science and technology, like the Global Positioning System, or GPS, let us build models and tools with greater precision and accuracy than was possible in the past. The North American datum of 1983, called NAD83, is the horizontal datum of the United States. NAD83 is based on a set of approximately 250,000 points. These points have positions that were determined both through the extensive triangulation network established over decades and newer GPS observations. All of these points were constrained to a geocentric origin, specifically the center of an ellipsoid model, which is a commonly used mathematical figure approximating the shape of the Earth. With the help of more recent satellite-based observations, we now know that NAD83 is misaligned to the most modern definitions of latitude and longitude by over 2 meters. Our ability to detect this misalignment comes from the current, more accurate understanding of the true center of the Earth. This offset causes many inconsistencies in mapping products referenced to NAD83 versus the datum based on the true center of the Earth. Looking at the vertical reference frame, the North American Vertical Datum of 1988, or NAVD88, is based on an extensive network of leveling observations from across the country. To make the network of observations internally consistent, one value was held constant, the local mean sea level value at Father Point, Rimouski, Quebec, Canada. Every leveling observation includes some random observational error as well as theoretical errors. While this averages out to less than 0.5 millimeter per mile, these errors actually accumulate to a total error of more than 1 meter between Miami, Florida, and Seattle, Washington. Additionally, the NAD83 positions and the NAVD88 elevations are inconsistent with the more accurate, up-to-date models that have evolved with advances in technology. These up-to-date models allow us to create a more accurate reference frame than the surveying methods and tools used in the past. Because we still need to use NAD83 positions and the NAVD88 elevations today, we have to artificially alter the updated models to fit with the existing reference systems. Much of the NAD83 and NAVD88 reference systems rely on marks in the ground that you must be able to physically access. Unfortunately, this physical infrastructure deteriorates over time. Marks often get disturbed. Sometimes this is accidental, as when landowners inadvertently destroy a mark on their property. Other times, marks are destroyed when roads are rebuilt or widened. Marks are intended to be very stable, so we attach them to the earth as permanently as possible. However, physical events like frost heave or subsidence can move a mark if it is not attached to something more stable, like a deep bedrock structure. Any motion of a mark requires that coordinates be updated over time, an expensive and time-consuming task. We do have strategies for replacing marks that are about to be disturbed or destroyed, but it takes time and effort. It would be prohibitively expensive to duplicate the level of physical effort and labor used to create our current datums. To address the problems with the physical infrastructure of our current datums and to integrate information from the most current technology, NOAA's National Geodetic Survey plans to establish new datums to replace NAD 83 and NABD 88.
You guys can understand more about the enormous amount of effort that goes into creating these models that we sort of take advantage of. You know, where are you? What's your elevation? Those seem like pretty basic understandings of space, but they're really, really labor intensive to create. So if you want to learn more about geodesy or datums or where you are, it's a good source. It's got a lot of different stuff on it. But okay.
How does the shuttle radar topography mission fit in? Didn't that make like the global, like actual surface model of the Earth?
Yeah. So this is an effort by NASA that uses when we were still using space shuttles. It flew over and did a radar beaming down radar to get a more accurate surface elevation model. But it's not totally accurate. It's pretty good. I don't know what the error on it is. But that's a digital elevation model as opposed to trying to do, I guess, a gravitational elevation model, which these are. But we'll get to that. That's a raster resource that you can get globally to get an elevation model, which is a great thing to have access to. But we can compare what the error is on that versus the vertical data. I bet the error is a lot greater on the radar mission. For instance, on the radar, you can see in some places where like a field has been cleared because the radar doesn't penetrate the same into a canopy as it does down. It's not getting the surface bounce back. It's getting interference with the trees. So you can see when you look at SRTM data really closely where there's a line between a field and a forest. So it's not always getting ground surface. There's another, Aster produced another DEM. Globally, SRTM, you can only get it at 90 meter resolution. Aster produced a 30 meter resolution product, but it also is full of problems in different places. Another problem you get with those products is that in highly mountainous areas, you get a lot more problems because you think about a mountain and you're getting a bounce back. You're getting a lot of there's a different surface area, so different slopes and different elevations within a particular pixel. So you can have a lot of problems in mountain areas. Because we're getting close here, I don't really think we should start another lecture. But we're going to talk quickly about some of the properties of geographic data on Thursday, and then go into working on doing some different analysis in ArcGIS, doing different kinds of queries, which is a powerful tool in ArcGIS. And that's what your lab this week will be on. Okay, so if you guys have particular questions that you want to ask me, I'll stay here for like 15 minutes. And I'm sorry, I'm going to email you guys all your labs. I was trying to print them and write notes on them, but I'm just going to email them